Hello and welcome to today's lesson on the motor effect, which is part of the magnetism and electromagnetism topic in GCSE Combined Science Physics. So in today's lesson we're going to try and understand what the motor effect is. So if we've been successful and learnt in today's lesson, we can describe the principles of electromagnetism, link the properties of electromagnets to electromagnetism, describe the effects of the motor effect, and finally explain the motor effect, which links into the following part of the GCSE Combined Science Physics specification, Fleming's left-hand rule and electric motors. Now, a motor transfers electrical energy into the kinetic energy of a conductor. Now remember, we're converting electrical energy via work into a kinetic energy store. Now energy cannot be created, it cannot be destroyed, it can only be transferred. Now this particular situation of electrical energy to kinetic energy assumes that the motor is 100% efficient, which will be a closed system. However, in reality, motors are open systems, which means that there's always some unwanted energy transfer. There's always some dissipation of energy. So some energy, when work is done, will go to the internal energy of the surroundings. Now we've looked at this previously, but if we place a potential difference in a metal, we can create a current through this particular conductor. Now this leads to the electro part of the electromagnetism force, but when this takes place, the moving electrons produce a magnetic field due to their movement at right angles to that particular movement. Now this is the magnet part of the electromagnetism force. So as an electrical current flows through the wire, it creates a magnetic field around the wire. So the charged particles are all aligned in the same direction and so therefore produce a magnetic field. Now it's important to note you can work out the direction of the magnetic field with the right hand rule, and the magnetic field is always at right angles to the electrical current. So what we know is the electrical current creates an electromagnet due to the electromagnetic force. Now this is different to a permanent magnet because permanent magnets will always have a constant magnetic field, so are always magnetic and always have the same strength of magnetic field. However, an electromagnetism can change these properties. The strength of an electromagnet's magnetic field can be altered by the current, and it can also change the direction by changing the direction of the current flow. So this leads to the four basic principles of electromagnetism. Number one, when electrical current flows in a wire, a magnetic field is formed around the wire. The stronger the current, the stronger the magnetic field will be, and when a current stops flowing, there will be no magnetic field. When the direction of current is reversed, the magnetic poles reverse. So with these four basic principles of electromagnetism, we can lead to the motor effect. So to construct a motor, you need two pieces of equipment. Firstly, you'll need an electromagnet, which is normally a piece of electrical wire which we could call a solenoid. Now remember, when a current has passed through the wire, it produces a magnetic field. The stronger the current flowing through the electromagnet, the stronger the magnetic field. No current flowing through the electromagnet, no magnetic field is produced. Change the direction of the current flowing through the electromagnet, the polarization of the magnetic field switches direction. Now electromagnets tend to be made out of thin, light pieces of wire, for example copper. Now the second bit of equipment you will need is a permanent magnet, a material with a constant magnetic field. So a common example of this is a horseshoe magnet. Now in a permanent magnet, it can never change its magnetic field strength, and it can never change its position of north and south poles. Now permanent magnets tend to be made out of heavy dense materials, which makes them difficult to move. So a horseshoe magnet can be produced with two bar magnets and a metal chassis, which produces a permanent magnet. Now like in a bar magnet, in a horseshoe magnet, the magnetic field lines are drawn from north pole to south pole between the two poles of that magnet. Now we say in this situation the magnetic field between the poles of the horseshoe magnet is uniform because the lines are parallel. Now it's important to know that when a conductor cuts through a magnetic field line, it produces a potential difference in the conductor. But that's not what we're going to look at in today's lesson. Because what we know is if we place an electromagnet inside the magnetic field of the permanent magnet, as the electromagnet magnet and permanent magnet are both magnets, their magnetic fields will interact with each other, the opposite poles will attract and the like poles will repel. So in this situation, the like poles of the electromagnet and the permanent magnet will repel each other. So as a result, we get our repulsion, and therefore a repulsive force will be experienced by both the permanent magnet and by the electromagnet. Now this force is only experienced by the part of the electromagnet which is perpendicular to the magnetic field. It's important to note that the part of the wire which will be parallel to the magnetic field does not experience a force. We'll consider that in upcoming lessons. So what we can say is the magnetic fields interact and create a pair of forces which act in opposite directions. Now what this will cause is it will cause the coil to rotate. So the force acting upon the electromagnet will cause it to rotate. So because it's rotating, we say the force produces moments which can cause the coil to rotate. So this idea is called the motor effect. Now you might think, well, why is it that it's the electromagnet that's moving? Well, the permanent magnet should also experience that same force and should also move as well, but it'll only move a little bit as it has a lot more mass compared to the electromagnet. Now eventually this will cause the opposite poles of the electromagnet and the permanent magnet to line up with each other. Now when this takes place, okay, when the conductor carrying a current is placed into that magnetic field, the conductor will exert a force on the permanent magnet, and the permanent magnet will exert a force on the conductor. This resultant force will cause your acceleration of your motor. However, when you achieve north and south pole aligning with each other from the electromagnet and the permanent magnet, neither side of the electromagnet would want to move because it's attracted to the sides of the permanent magnet. So eventually when the north poles and south poles align and attract, your coil would no longer move. So what we do is we compensate for this by adding a device called a split ring commutator. Now this device flips the magnetic field of the electromagnet by changing the current as it reaches half a rotation. So what it does is the split ring commutator must change current flow direction every half a rotation to ensure the poles of the two magnets are always repelling each other. Now this means that if the commutator was not found in the motor could only rotate for half a rotation before you get attraction and therefore no more movement for your coil. So what happens is the two halves of the commutator swap from one brush to the other. This reverses the current in our coil and keeps the forces acting in the same direction. You've always got this repulsive force. So this will allow your coil to complete a full rotation. So what does a commutator do? It changes the direction of the current flow, which means that it flips the magnetic field direction of your electromagnet, and this happens every half a rotation to allow for a full rotation of your motor to take place. Now we use graphite as our commutator because graphite is an electrical conductor, and in addition it's very, very slippery as there's weak intermolecular forces of attraction between the layers of graphite, so it causes very little friction when in contact with the rotating commutator, which makes the motor very efficient. So this leads to our idea of a DC motor. The direct current motor is the motor used throughout the world today in many different devices such as cars, such as fridges, such as anything which can use an idea of turning electrical and magnetic energy into motion. So we can use our direct current motor in many different situations. So let's just clarify what's going on. An electromagnet is placed inside the magnetic field of a permanent magnet. The sides of the coil parallel to the magnet experience a force in opposite directions, and the forces cause moments that act in the same with either clockwise or anti-clockwise direction. The moments cause the coil to rotate, and this is a motor. Now every half revolution the two halves of the commutator swap from one brush to the other brush, so the commutator reverses the current in the coil, keeping the forces in the same direction to allow the coil to keep rotating. Now in the real world we don't actually have a wire, rather many electromagnets placed inside permanent magnets are actually coils of wire. This is because coiled wire gives a stronger magnetic field for your electromagnet, and this gives the motor the potential to rotate very quickly. So here's a more a more familiar layout of an electrical motor. This is a schematic looking over the top of the motor. Now you'll notice you've got your coil in the center between the north pole and the south pole of the permanent magnet. Now a split ring commutator is placed on the circuit to allow it to fully rotate. Now you've got your electromagnet in the middle and the permanent magnet to the side. Now it's important to note that as the coil is moving around the coil, it will move in different directions because it will leave your plus and will go to your minus, so we can actually consider our coil of our electromagnet as two different sections, section 1 and section 2. Now it's important to note we don't have to consider the top and bottom sides of the coil as they are parallel to the field lines of the permanent magnet, so experience no attraction or repulsion. So we've only got to consider section 1 and section 2 of our electromagnet because they're perpendicular to the magnetic field of the permanent magnet. Now in each section the current is flowing in an opposite direction, so the magnetic fields they produce are in opposite directions. This means the two sections, the sides of the coil, experience the same interaction, repulsion, because they're next to the different poles of the magnet. So this means that if their forces are in opposite direction, this allows the coil of the wire, the electromagnet, to rotate. Now it can be easy to visualize the repulsion by thinking of an experience between the electromagnet and the permanent magnet as a force between the two. So let's just clarify that this repulsive force links to a resultant force on our electromagnet, which will cause an acceleration on our electromagnet. Now, like we said before, section 1 and section 2 experience a magnetic force in opposite directions, which gives our resultant force. Now, please remember the force due to magnetic interaction between the two magnets is a non-contact magnetic force, but this magnetic force produced causes the electromagnet to spin, and that is how we get our motor to spin. Now the larger the magnetic force, the faster the motor will spin. Now it's important to note that the magnetic force can be increased by increasing the current through the electromagnet, increasing the magnetic field strength of the permanent magnet, or increasing the length of the current carrying wire in the field. So, when a conductor carrying a current is placed in the magnetic field, the magnet producing the field and the conductor exert a non-contact magnetic force on each other. This resultant force causes the acceleration of the motor. Now, when considering the forces, the coils spin because there's a force due to the motor effect on each side of the coil, but these forces act in opposite directions. Now, remember there is no force when the two magnets are parallel with each other, but there's the greatest force when the two magnets are perpendicular with each other. Now the magnetic field, the current and the magnetic force are all perpendicular or at 90 degrees to each other. So we can consider our current, magnetic field and magnetic force in the following configuration. Now the magnetic force and current being perpendicular to each other is a key concept of electromagnetism. So it's important to think about these ideas, but also as well that the magnetic force and the magnetic field are perpendicular to each other. Now there is a trick to learning the direction of movement in the motor effect, and it is called Fleming's left-hand rule. Now Fleming's left-hand rule shows you the direction of movement on a conductor carrying a current in the magnetic field. This allows you to work out the direction a wire moves in an electromagnet, and this force can cause the wire to move. So the first thing you do is with your left hand you stick your thumb up. Now the thumb shows the direction of the magnetic force and therefore the movement of the wire. The first finger, which you will point outwards, shows the direction of the magnetic field from the north pole on the knuckle to the south pole on the nail, and then finally with the same left hand you will swear with your middle finger, and the second finger, this middle finger, shows the direction of current from the positive on the knuckle to the negative on the nail. Now we can use this trick to work out the direction of each of these components. So you've got your magnetic force, which leads to the movement, the magnetic field and the electrical field, which is due to the current. So Fleming's left hand rule shows the direction of movement on a conductor carrying a current in a magnetic field. This allows you to work out the direction of the magnetic force, and the magnetic force causes movement. The first finger on your left hand represents the direction of the magnetic field from north to south pole. The second finger represents the direction of the current. The direction of the current is in the direction of conventional current, positive to negative by the way, and the thumb represents the direction of thrust or resultant motion in your particular consideration. Now, how do you use this in a question? Well, if you're given a motor in a question, the first step you do is you place your knuckle of your first finger at the north pole of the permanent magnet and point your finger to the south pole of the permanent magnet. You then place your second finger pointing in the direction of the current flow, and you may have to reorientate your finger to ensure step 1 and step 2 are satisfied simultaneously. And then finally, the direction that your thumb points into is the direction of the magnetic force and the direction of the movement of the wire. So what have we learned in today's lesson? When a conductor carrying a current is placed in a magnetic field, the magnet producing the field and the conductor exert a force on each other. This is called the motor effect. Now, you should be able to show that Fleming's left-hand rule represents the relative orientation of the force, the current in the conductor and the magnetic field. And you should be able to recall the factors that can affect the force on a conductor. Now, you should also be aware that a coil of wire carrying a current in a magnetic field tends to rotate, and this is the basis of an electrical motor. And you should be able to explain how the force on a conductor in a magnetic field causes the rotation of the coil in an electrical motor. So if we've been successful and learnt in today's lesson, we should be able to describe the properties of electromagnetism, link the properties of electromagnets to electromagnetism, describe the effects of the motor effects, and finally explain the motor effect. So I hope you've enjoyed today's lesson on the motor effect, which is part of the magnetism and electromagnetism topic in GCSE Combined Science Physics. Thank you very much for listening and have a lovely day.